Welcome back to Lecture 5. This is the last part of Lecture 5 in which we'll be discussing collisions and conservation laws. We're continuing to develop the ideas of dynamics in Einstein's world, and collisions and energy momentum conservation is a good way to do that. Of course, in this discussion, we'll be converting energy to mass and mass to energy. We'll be creating and destroying elementary particles. So we'll see another illustration that in relativity, the expression of energy conservation allows these processes to occur, and in field theory and quantum field theory in particular, they're predicted and they're an essential part of the theory. So let me remind you a little bit about this. We'll be imagining an initial state of a couple of particles coming into an interaction region. I've integrated it. I've shown it as a hashed area, and then some particles coming out. Now, we're not in a position, we don't know enough about dynamics to look inside the hashed area, but toward the end of this course, when we know about Maxwell's equations, we'll be able to do a little bit better. But we are able to discuss the conservation laws that control the initial state and the final state when the particles are very far away from one another and you can ignore the interactions between them. Okay? And so we want to look at some interesting cases, and so we'll want to look at light coming in. And remember, for light, we've stated that in that case there's a relationship between the energy carried by light, okay, and the momentum carried by light. The magnitude of the momentum is that E is equal to PC. We saw in general that for a massive particle we had the energy momentum relationship, and this is the relationship that occurs when the mass of the particle goes to 0, and E is equal to PC. P is the magnitude of the 3 vector P, and we'll be obtaining this relationship later in the course, but we've sort of seen bits and pieces of it already. Now also we'll want to look at quantum physics collisions, in which case we don't have a wave of light, we might have a particular photon. And for a photon, we have the basic relationship from quantum mechanics, that the energy of a photon is related to its frequency, and the proportionality is Planck's constant. H is equal to 6.63 times 10 to the minus 34 in MKS units. Okay, and we'll use those two facts to make an interesting phenomenology. Okay, so that's the idea of it. We're just looking at the initial state and the final state, and recalling that we should have energy momentum conservation, and let's see if we can figure out how things scatter on that basis. Okay, remember we've seen that energy momentum is a 4 vector. So a 4 vector is a vector that transforms like x and t. All of the components mix under boosts. So if you're going to have energy momentum conservation in one frame, you can have it in another frame, but you have to anticipate that energy and momentum will be mixing. And that's given by the Lorentz transformation for energy momentum, and we've written down those formulas already. So here's an example of a photon of energy Q is absorbed by a nucleon of rest, and it has a mass m naught. Well, it might be a nucleon, it might also be an atom, okay? Whatever, it doesn't matter, we're just doing energy momentum conservation. We're not delving into the particular dynamics of the beam or the target. So here comes a photon coming in from in a beam, and here's a target. It's a particle of mass m naught in its rest frame. That's the initial state, and then they collide, and then the final state, the photon is absorbed, and you see an excited state of the m naught. Call it a mass m prime, and it recoils to the right with a velocity v. That's the final state. Now it might be that m naught is an atomic state at some level, and m prime is an excited state of the atom, and you calculate the energies by doing some quantum mechanics. maybe they're the excited states of hydrogen, for example, and you know the Balmer series of hydrogen, and you know what the possible physical states are. So anyway, we're going to do just kinematics here, and so I'm going to conserve energy, and I'm going to conserve momentum. Well, what's the energy here? Well, the energy is the energy of the photon plus the rest mass energy of the target, and that's equal to the final state, which is a recoiling mass m prime, and so I've written that down here, right? So gamma here is the gamma factor for this state that has velocity v. So gamma is just 1 over the square root of 1 minus v squared over c squared. Okay, that's energy conservation. And momentum conservation, well, we have the momentum of the photon, that's q over c, right? Because it satisfies the energy momentum relationship of light. You divide the energy, the relativistic energy, by the speed of light, you get the momentum. So q over c is the momentum of the light coming in. The target is at rest, no momentum, and then the target is excited and recoils. It has a momentum gamma m prime v, just recalling the equation for the momentum. Well, now I can solve this. I can solve this problem. I can find what are the potential excited states that I can excite by bringing in an energy of q. Okay, so that's what I'm interested in. I want a formula for m prime in terms of m naught and q. Okay, well, so I can go back here in the conservation of momentum and find v over c in terms of q and m naught, just like that. Okay, just using for this formula both momentum conservation and energy conservation. Okay, and then knowing that, I can write down what m prime is. I can solve for m prime by combining these two formulas. Okay, and then I can use the previous formula to get rid of the velocity dependence in favor of q and m naught. And a little bit of algebra that I'll ask you to check, one line, is that m prime is then equal to m naught times the square root of 1 plus 2q over m naught c squared. Okay, so m prime isn't just equal to m naught c squared plus q. We see that here that m prime c squared is less than m naught c squared plus q. In other words, the energy of the excited state is less than the energy of the initial atomic state plus q. Okay, and that's because some energy is just going into the recoil. This fellow isn't produced at rest. That would violate momentum conservation. It recoils to the right. It has some velocity, and so not all of the energy is available to go into m prime. Some of it goes into v, and we see that in these various formulas. Well, for example, here it is that m prime. Put the c squared over here, and see m prime c squared is equal to q plus m naught gamma squared divided by gamma. Gamma is always greater than 1, and so m prime c squared is always less than m naught c squared plus q, and the details of it are contained in the last formula. Okay, so some energy goes into recoil, and in order to find an excited state m prime, we're going to have to adjust q appropriately. Okay, so that's just one example. It's interesting to take that process and turn it around. And so I might begin with an excited state of the atom or the nucleus. It's just sitting there at rest. I call the mass m naught, or the energy of the state m naught, right? M naught c squared is the energy of the state, right? In relativity. And then there's photon emission from the excited atom. A photon, I say, goes off in one direction. I choose that to be the plus x direction, and so the atom or the nucleus recoils in the opposite direction with a potentially lower mass, okay, and a velocity v, and q goes on afterwards. So again, I want to know how to relate the energy of the photon, okay, to the mass difference between the initial state and the final state. Okay. So I'll hone in on those things by writing down energy conservation. Well, what's the initial energy? Just m naught c squared. It's m naught c squared because this fellow is at rest. So the relativistic energy is just rest mass times c squared. In the final state, okay, I have this state m prime. I call that an energy E prime. Okay, and there's also the energy of the photon. Then I have momentum conservation. Well, initially there's no momentum at all. It's just a particle at rest. So 0 is equal to the momenta afterwards. The momenta afterwards is the recoiling momenta of the atom. Okay, and then there's the momentum carried by the photon in the opposite direction, so that those two quantities subtract. Okay. Now I'll use the fact that this recoiling m prime is constrained by the energy momentum relationship for that particle. So see, I have E prime in here. Okay, I have P prime as well, but they're related because this is a relativistic particle of mass m prime, and so its energy and its momentum are given by the energy momentum relationship that we've already derived. Okay, so I write down that energy momentum relationship, and I just stick in here E prime from energy conservation, get rid of that. And then I get rid of P prime from momentum conservation, put those in there, do a little algebra, okay, and I can solve for Q in terms of the energy difference between the initial and final state. So I'm defining delta E to be m naught minus m prime. Okay, just the energy differences. Put the c squares in there. Okay, so delta E is the energy difference between m naught, which is an excited state that can spit out a photon, and m prime, which is a less excited state, or perhaps the ground state. Then you do the arithmetic, and you see that Q is equal to delta E with a correction factor due to recoil, which is 1 minus delta E over 2 m naught c squared. Right? If there were no recoil, of course, then the photon would have all the energy available, which is just the difference in the rest mass energies of the nuclei or the atoms. But that's not quite right, because you have to have momentum conservation. This fellow comes off with a momentum, with a velocity v, okay, that matches the momentum carried by the photon q. That's this equation over here. So the arithmetic gives me this here. So we see that q is less than the atomic energy spacing due to recoil. But we see we can make that difference very small. For example, let's just imagine that m naught is very, very large. Okay? Then the momentum due to recoil is very, very small. It's suppressed by a 1 over m naught, in which case q is almost just the good old energies between the two states. Well, in the Mossbauer effect, you really make that equality as close as you possibly can. In the Mossbauer effect, you put the excited atom into a crystal, and so when it decays and photon emission occurs, the momentum of the photon is shared throughout the whole crystal, okay, and so that's reflected in a tiny recoil velocity of the emitting atom, because it shares its momentum with the entire crystal. Well, you have to arrange things properly. The momentum is not so much that it pops the excited atom out of the crystal, and there's some technical considerations like that, some crystallography to be careful of there. But you can do it, and then you have the Mossbauer effect, in which case the recoil is absolutely tiny, and to very good approximation, the photon energy here is the difference of the energy of the two states. If that's the case, then you can use this mechanism to study the spectral line shapes, the quantum mechanics of the two states m prime and m naught. You know, in quantum mechanics, the line shapes will have a certain breadth because of the uncertainty principle, and you might want to investigate the line breadth, and then you can do it with the Mossbauer effect because it's very precise probe into the energy difference between the two states. I bring that up because later in the course, in general relativity, we'll use the Mossbauer effect to investigate the equivalence principle of general relativity. It's a famous experiment that did that, and we want to lay the groundwork for that discussion by telling you a little bit about the Mossbauer effect. Mossbauer effect is discussed more thoroughly in the textbook, so take a look at it. But the basis for it is just the kinematics. And here we've done it properly and fully, and you can learn about how it can occur within a crystal. So that's one example of energy, momentum, conservation, and relativity. Let's take another one, but now let's move up to a modern accelerator where you might collide a couple of protons together and try to create new states of matter. Well, I'm not going to do anything terribly exotic. We'll just take an old-fashioned one from the 1930s. We'll imagine a proton-proton collision to produce a proton and a neutron plus a pion. A new particle, a pion, that's called the carrier of the nuclear force, and we'll want to study it and understand its properties, its quantum numbers, its mass, and everything like that. Okay, we want to produce it in the lab so we can study it. Some facts about the masses involved here. The ratio of the mass of the pion to the mass of the proton is about 0.149. It's a pion's a light particle. And then in addition, the mass of a proton is approximately equal to the mass of a neutron. A small difference between them due to electromagnetism and weak interactions. But for the purposes of this calculation, saying that they're equal is good enough for us. And the mass of a proton in energy units is 938 MeV. Right, so I don't write down the mass, I write down m sub proton c squared, because that's what enters my equations here. And high energy physicists do this all the time. They use the energy equivalent of a mass, because that's what will enter their formulas in the first place. So I say that so I use this loose language that a proton weighs, 938 MeV. I'm really writing down the energy equivalent of it, and I'm writing down thinking about inertial mass. Okay, so then I might want to construct an accelerator, a proton-proton accelerator. Protons have a positive charge equal and opposite to the electron. I can accelerate them in a cyclotron or a betatron or whatever. I'm thinking about the old days when this experiment was news, the 1930s. I'm at Berkeley. Okay, my name is Lawrence or Livingston, and I'm trying to create new states of matter using accelerators of those days. Okay, and then I definitely want to know what's the minimum beam energy required to make a pion, right? It's tough for me to make these accelerators. It's 1935, and so I really have to worry about things like that. Well, these days you worry about things like that also, but you're in the realm of the Large Hadron Collider, where the center of mass energy might be tens of TeVs, trillion electron volts. Okay. Well, you might think about this in the center of mass frame. Well, I'll have a couple of protons with each other having a velocity u, coming at one another and colliding. That's my state before. Okay, they crash into one another, and then they make a final state of a proton, a neutron, and the pion, which we want to study. Okay, that's a process that's allowed by the rules of nuclear physics, and we're going to, of course, conserve charge when we do that. In the initial state, we have two charges. In the final state, we have two charges. The neutron is neutral, of course. So we'll write down energy conservation. Here's energy conservation for the two protons coming against one another. They have the same energies of gamma mc squared. So 2 times that is the initial energy. In the final state, well, the final state's defined as the lowest energy state that allows for the existence of the three particles. So they're going to be produced at rest in the center of mass. Okay, and you just have the total energies, that's the rest energies of the three particles, and I've written that here. Okay, so therefore I can solve for gamma. Gamma, that's the gamma associated with the beam, okay, of the initial state. Gamma is 1 over 1 minus u squared over c squared as usual. And I can solve for gamma. I see it's this ratio of the masses. Okay, I know the mass of the pion. And gamma is slightly bigger than 1, 1.074. And then I can take that number and solve for u over c. Right, gamma is just 1 over the square root of 1 minus u squared over c squared. So just do the arithmetic and you'll find that u over c is approximately 0.37. So the protons have to be going at a pretty good rate, a pretty good speed, okay, a little bit more than a third the speed of light, and then they can create the pion in the final state. And that's how you do it in the center of mass. Now in the old days, this wasn't a practical experiment. The practical experiments was to take a beam of protons, accelerate them, and knock them into a target which is stationary in the lab. So that's shown in this situation, the lab frame down here. But you see, I solved the problem in the center of mass frame. I can get to the lab frame just by making a boost. Okay. In the lab frame is shown here, and then here's the center of mass frame. Okay, and they're related by a boost through the velocity u, right? Right? Because you see, I'll make a boost such that this particle, okay, in the lab frame goes to rest. So it's a boost through the velocity u. Okay, so therefore I see that my velocity v of this particle, you see, is just the velocity of this particle except boosted by through a velocity u. Okay, and so therefore I know how to calculate v for this particular physical configuration. I just boost it through a velocity u, and then I'll get the picture in the lab frame from the picture in the center of mass frame. But remember, when you add velocities in relativity, you have a nonlinear expression to deal with. So I go back and I look at that expression. I'm careful with my pluses and minus signs, and I see that v is equal to u plus u divided by 1 plus u squared over c squared. That's just the addition of velocities in this particular situation. Okay, which is clear from the picture here. I just have to make a boost, okay, so that this particle becomes the at-rest target particle. So I'm boosting to the right by velocity u, okay. So that enhances this velocity, okay, and it grows by u plus u, and so it's u plus u addition, but corrected for special relativity. So there's the denominator in there as well. So that gives me what v is. But I know what u is. It's about a little bit more than a third the velocity of light. Okay, and so I just plug into that formula, and I find that v is slightly less than 2/3 of the speed of light. Okay, very reasonable. Okay, so now I can ask, what's the relativistic kinetic energy of the beam? Okay, so that's the relativistic energy of the beam, and subtract off the mass of the beam. Okay, and so plugging in the numbers there, okay, I'll get 290 MeV. So the relativistic kinetic energy of the beam is 290 MeV, which is more than twice the rest mass of the pion. Okay, so what I learned from this, I learned that because of momentum conservation, a lot of the energy that I bring into the beam just goes into momentum conservation of the final state particles, and I don't have all that energy available to create the pion, only a bit of it. Okay, so making the particle in the lab frame is much less efficient than making it in a colliding beam experiment, a colliding beam accelerator, and so I have to make a more powerful accelerator to make this beam here than I do to make these colliding beams up here. So that's why that's why, for example, CERN, the Large Hadron Collider, to look for new massive states of the Standard Model, they discovered the Higgs boson in 2012, remember? And that's a colliding beam experiment with a proton impinging on another proton, each of them in the lab having a energy on the order of 5 or 6 or 6 and a fraction TeV, and colliding head on like this to try to make new states of matter, and in that case terribly successful in 2012 to find the Higgs particle, the particle that's responsible for some of the masses of elementary particles in the real world. Okay. So there are lots of examples now. Okay, in your textbook, there's a flood of examples and a flood of problem sets and solutions to some of the problem sets, and you'll do kinematics. Okay, you'll get used to energy momentum conservation and relativistic kinematics, and it's very worthwhile to do that. Throughout those problems, you'll learn that there are more sophisticated and efficient ways of doing the calculations by exploiting the invariance of the dot products of 4 vectors. Okay. We already noted that if you take a 4 vector and take the inner product of it with itself, you get the energy momentum relationship, and you generate an invariant. We also noted that if you take one 4 vector, let's say the 4 vector of energy momentum 4 vector 1 particle, and you take the inner product or the dot product with the 4 energy momentum 4 vector of another one, okay, you'll get a invariant. Okay, and so you're able to take like P1 dot P2, and you can, it's an invariant, so you'll evaluate that in whatever frame is convenient for you. Maybe the center of mass, maybe the lab frame, maybe some other frame. And using the invariance of these scalar products, you can very easily get to the solution of some of these kinematic problems without having to delve into the details of Lorentz transformations, which is kind of tedious. So check out some of those problems, and check out some of the solution sets of those problems, which are included in one of the lengthy appendices in the textbook, and you'll become pretty slick at doing energy momentum kinematics, which is really essential if you're interested in high energy physics. Well, let's make some comments now about other collisions that you might imagine, and I'm thinking now in terms of the fact that we're going to be looking at electrodynamics in more detail. So let's look at some electromagnetic collisions, and in this case, let's imagine that we're dealing with a quantum theory. So we're dealing with photons. Okay, E equals h nu, the quantum of the electromagnetic field, and we scatter individual quantums of photons off of electrons and what have you. And in this case, then, using the fact that electrodynamics is amenable to perturbation theory, okay, we can calculate scattering amplitudes and scattering cross sections as a Taylor series expansion in a small parameter, which is called the fine structure constant, E squared over h bar c, which presents itself in the quantum formulation of electrodynamics. It's a small parameter, about 1 over 137. 137 is one of those numbers that every physicist knows full well. And the smallness of 1 over 137 allows you to do perturbation theory in quantum electrodynamics. So I might be looking at photon-electron scattering, and then if you're doing quantum electrodynamics, then you develop the perturbation theory of it, and you develop the pictures of covariant perturbation theory, the great discovery and development of Richard Feynman. Okay, and you draw little pictures, and these little pictures have rules which tell you how to calculate the probability amplitudes involved. Okay, so I have a photon coming in, an electron coming in. The photon can get absorbed, right? It's the quantum equivalent of light getting absorbed by a material. Okay, in this case, the photon gets absorbed at a point, and then an electron recoils off. Okay, and then rather quickly thereafter, it spits out a photon in another direction, and you have the scattering of a photon and electron to a photon electron. Now there are other processes here, so I wrote plus dot 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 to indicate that. We're not doing quantum electrodynamics here, but we're just indicating that now you can look inside the blob in our previous pictures, the interactions blob, and if you have a theory of the dynamics, you can make a picture of it, and Feynman does that here. And what Feynman does, and what was great about his formulation of quantum electrodynamics, is that it makes manifest energy momentum conservation, locality, and causality. Okay, the photon's absorbed by the electron at a point. Energy momentum is conserved at that point. When this emission occurs, again, it's an interaction at a point. Okay, the electron comes in, electron goes out, it pushes against the photon in some sense, and energy and momentum is conserved here, which guarantees that energy momentum is conserved for the overall process. Okay, that's one of the aspects of Feynman diagrams. Okay, so locality and causality played a crucial role in that development, and we're going to find that in our classical physics discussions and our derivation of the Maxwell equations, that we'll be using locality and causality in the context of simple differential equations to make this point come alive for us. Now, it's interesting that in collision you can find new processes, and this is what happened, of course, in the accelerators in the 1930s. They created new states of matter. Okay, they collided protons together and they made a new state of matter called the antiproton. Well, I can do something similar here in my electrodynamic collisions. I can make a collision that's energetic enough so that this photon doesn't come out, but rather the photon couples to a new state of matter called a positron, and a positron and an electron come out. They're created at a point. Energy momentum is conserved throughout the entire process, and I create a new state of matter. Right? That's what you're shooting for when you make a collider, when you make an accelerator. Okay. So we find some new processes, and that brings up the question of whether the quantum electrodynamics has all the properties of electrodynamics that we hold so dear. One of the properties of classical electrodynamics that's essential in our discussion is, of course, linear superposition. Okay, and you've seen that many times in your freshman and sophomore physics. That if you solve a problem for the electric field, say, for a certain charge configuration on the one hand, and then you do a similar problem and calculate and solve for the electric field in a different charge configuration, that now you have this, now you can bring those charge configurations together, okay, and the electric field of the two charge configurations will be the sum of the two electric fields for the individual charge configurations, okay? So the electric fields add without any additional complication, okay, and that's called linear superposition, and we'll review that later in two more lectures. Okay, so that brings up, so in these pictures, that would be that photons pass through one another without interacting, right? It's a linear system. They don't notice one another. Electric fields add, okay? There's no interaction between them, and that's the end of the story. So we can question whether that happens in the quantum theory by doing some experiments. One experiment we might do is to take two photons in the initial state, aim them at one another, okay, and see if they interact. Do they come through the interaction region with the same energy and momentum that they initially had? That would be the quantum equivalent of linear superposition. Well, in fact, we find that in quantum electrodynamics there are sources of non-linearities, and I've shown you one here, okay, where you can make a virtual loop of electrons and positrons around like this, and so the incoming photons and the outgoing photons can couple to that loop, and so there's no reason for the energy momentum of this fellow to be the same as the energy momentum of that fellow. They can swoosh around through this this loop, and the loop being possible because of the existence of antiparticles. And I put plus dot 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 because there are other Feynman diagrams that can contribute to this. So one of the things we learned that is there are quantum corrections which are proportional to the Planck constant, which violate linear superposition of the classical theory. Okay, so it's fun to just make these pictures and discuss these scattering processes from this perspective. We're not going to do anything more with it, but it just lays down the landscape for later courses that you'll take in quantum mechanics and in relativistic quantum mechanics, okay, where the linear superposition principle of the classical theory will be just a good approximation in various cases. And you have some interesting new phenomena that comes up because in relativistic quantum theories where you've unified relativity with quantum mechanics, there are new phenomena. One of the new phenomena is the existence of antiparticles. And once you have the existence of antiparticles, you have the possibility of pictures like this. Okay, and those sorts of pictures where a photon can become a virtual state of an electron-positron pair, as shown here. See this? I've taken this possibility here. I've drawn it out in 1, 2, 3, 4 places and connected the electron and positron lines appropriately. Once you have that process, then you have sources of non-linearities, scattering, and new phenomena posed to you. What's interesting is that the existence of the antiparticles that make all of this possible is a consequence of quantum mechanics, relativity, and locality. Okay, it's a very fundamental property of space-times, and it's something that we'll be looking for when we pass to the quantum version of the classical field theories that we're studying in this course. Okay, so that's enough for dynamics as far as we're going. Now we want to return to the thrust of this course. Okay, to understand acceleration and forces, and gradually push our way toward Maxwell's equations, and that's what we'll pick up in the next lecture.